Hi, today we have a fantastic integral to work through. It looks innocent and simple enough, but trust me, there's a lot going on here. A lot of substitutions are going to be taking place, and hopefully by the end of it, I won't be so tired that I'll need a substitution for myself. So let's see what we're dealing with. We want to determine the integral of the root of tan of x dx. Our first maneuver will be to make a simple substitution with u being the root of tan of x. Squaring both sides gives us u squared equals tan of x. Differentiating gives us 2u du equals secant squared of x dx. Rearranging for dx leaves us with 2u divided by secant squared of x du. And now secant squared is just tan squared plus 1. So we have dx equals 2u over tan squared of x plus 1 du. Looking back up here, tan of x is u squared. So tan squared of x is u to the 4. So this will replace with u to the 4. And now we can make our substitution for u up here, and for dx we can put that up here. So our integral now looks like this. And touching this up just a little bit, we end up with 2u squared in the numerator over u to the 4 plus 1 du. Now there's no immediate method that will help us to solve or integrate this. So what we're going to do is take a partial fraction decomposition of our denominator, or of our fraction. So here's what we have. First of all, this denominator needs to be factored. Again, there's no immediate method to even do that. So we'll have to pull some clever tricks. First, notice that u to the 4 plus 1 is the same as u to the 4 plus 1 plus 2u squared minus 2u squared. And when we shuffle things around a little bit, we now have those first three terms forming a factorable expression. So we can factor this in the following manner, with minus 2u squared at the back. Now this almost looks like a difference of squares. So to make it a difference of squares, we'll pull one more move. We'll write this as that. And so how does this difference of squares factor? We'll take the u squared plus 1 plus this times the u squared plus 1 minus this. Okay, great. So this u to the 4 plus 1, which is this denominator, can now be written as the following. Our integrand will be the following. So now we can work out our partial fraction decomposition. This is a quadratic factor of order 1. This is a quadratic factor also of order 1. So we can write our fraction here as one fraction with a linear term on top divided by our first quadratic factor down here, plus, same idea for the next fraction, cu plus d, a linear term, divided by this factor down here. Now we're going to take this and turn it into one big fraction. How we would do that is simply by the following. All over our denominator, which we can just write as u to the 4 plus 1. So our fraction here from our integrand now looks like this after we've started some partial fraction decomposition. Well, obviously the denominators match, so what's left to match is our numerators. So what we'll need to do is expand this out, collect terms, and then compare coefficients from the left side to the right side. So we'll need a little more room for that, so we'll move to the next board. So here we are now back at our next board. We'll just recall that this was our first substitution that we made, and where we left off was here, with our integrand being equal to this. So now, comparing numerators, we have the following. Let's expand au cubed minus root 2 au squared plus au plus bu squared minus root 2 bu plus b. And then, expanding over here, we obtain cu cubed plus root 2 cu squared plus cu plus du squared plus root 2 du plus d. So, let's look at our terms containing u cubed. Let's look at our terms containing u squared. Let's look at our terms containing u. And let's look at our constant terms, b and d. Our terms with u cubed, let's factor out u cubed. So we're left with a plus c. In orange, we're going to factor out a u squared, leaving us with negative root 2a plus b plus root 2c plus d. Then we have our terms with u. So factor out a u, we're left with a minus root 2b plus c plus root 2d. And finally, we have our constant terms. Okay, good. So we've worked this out. Now, the coefficients on the left-hand side have to match the coefficients on the right-hand side for these to be equal, the left and right. So what we notice is on the left is just a u squared term with a coefficient of 2. All other powers of u don't exist, so their coefficients are 0. So what does this tell us? First of all, this coefficient is 0. Since it's the coefficient of u cubed, we have no u cubed on this side. In orange, this is the coefficient of u squared, and we see that it must be 2. Next, this is the coefficient of u, but u on this side doesn't exist. Its coefficient is 0. So we have a minus root 2b plus c plus root 2d equals 0. And finally, these constant terms, there are none on the left side, so these must be 0. So now we're left to solve this equation with four equations with 4 unknowns. First thing we notice is b plus d equals 0. And in equation 2, we see b plus d. So this plus this must be 0. So if we sub equation 4 into equation 2, again, this inserted here gives us nothing, so we're left with negative root 2a plus root 2c equals 2. If we divide through by negative root 2, we obtain the following. But from equation 1, a plus c is 0, or in other words, c is just negative a. So we can now sub equation 1 into what we have above. So we have a minus, well, c is negative a. This means we have 2a here. Dividing both sides by 2 gives us a being negative 1 over root 2. So we can box that off. But remember, we just said that c is negative a. So this implies for us that c is the negative of this. So positive 1 over root 2. If we now sub what we've obtained down here for a and c into equation number 3, well, what does that give us? Well, here we have negative 1 over root 2 minus root 2b plus c, which is this, plus root 2d equals 0. Well, this plus this gives us nothing. And then we can divide through by root 2, or negative root 2, whichever you like. That gives us b minus d equals 0. Well, this tells us that b equals d. So we can take that fact and sub it into equation 4. So if b is just d, this is d. And 2d equals 0, meaning d equals 0. We can box that off. But of course, this implies that b is also 0, because we noted that b equals d. And if d is 0, b is 0. So there we have it. We obtained our 4 coefficients. So now we can rewrite our fraction from the previous board as 2 separate fractions, and we'll see that on the next board what that looks like. Okay, here we are back at our next board. So when we set up our partial fraction decomposition, we had our integrand being equal to this. Now we just found a, b, c, and d. So let's sub those values in. A was negative 1 over root 2. B was 0. c was 1 over root 2, and d was 0. So now, our integral looks like the following. We can pull out this factor of negative 1 over root 2. We can pull out this 1 over root 2. And now we look at these integrands, and again, nothing immediate comes to mind, no common method or process to handle them. So we're going to have to employ another trick here. We're going to complete the square for this quadratic and this quadratic in the denominators. So what does that look like? If we complete the square, we have u squared plus or minus root 2 of u plus 1. So we'll complete the square for both in one shot. So what does this give us? Well, looking at the first two terms here, we're going to take half of this second one, which is root 2 over 2, and square it, which is 2 over 4, or 1/2. So we get u squared plus or minus root 2u plus 1/2 minus 1/2. And then we have this lingering positive 1. Now the reason why we do that is because the first three terms here form a perfect square trinomial which can be factored. So a neat trick I like to use is I just take the root of this first one, I take the root of this last one, I use the sign that's in between here, plus or minus, square it all, and then what's left is this minus 1/2 plus 1, which is positive 1/2. And so here's what we have now. So these two integrals now are what? The integral of 2u squared over u to the 4 plus 1 du is, okay, negative 1 over root 2 times the integral of u divided by, well, u plus 1 over root 2 all squared plus 1/2. And then for this integral here, we have plus 1 over root 2 times the integral of u over, and now u minus 1 over root 2 all squared plus 1/2 du. Now here we're going to make another substitution. Let's let A be this quantity here, which implies that u is a minus 1 over root 2. And differentiating this, we get dA equals du. So for this integral, we have this substitution. For the other integral, and we're missing a du over here. For the one boxed in orange, let's let b equal this quantity in here, u minus 1 over root 2, which implies that u is b plus 1 over root 2. Differentiating this gives us db equals du. And so now, what we have boxed in green, let's see what that gives us. We have the integral of 2u squared over u to the 4 plus 1 du equals negative 1 over root 2 times the integral of, well, u, which is a minus 1 over root 2, divided by this quantity, which is a squared plus a half, du, plus this quantity in orange is 1 over root 2 times the integral of, well, u is b plus 1 over root 2 over this quantity here is b, so b squared, plus a half du. And so there's still more work to be done here, so let's pause and go to the next board. So here we are now back at the next board, and just to take note, at the last board I had left du here and du here, but as we saw, du over here was dA, and du over here was dB. So I've made those replacements. Okay, let's continue. What we will do now is take this first integral and break it up. We will break it up in the following fashion. We will take the integral of a over a squared plus a half dA plus the integral of negative 1 over root 2 over a squared plus a half dA. Doing the same thing to the second integral up here, we'll break this up in the following manner. We have plus 1 over root 2 times b over b squared plus a half, integral of that, plus the integral of 1 over root 2 divided by our denominator. The integral of 1 over root 2 over b squared plus a half dB. Okay, so we will need to make some more substitutions at this point. Over here and over here, where the numerators are a and b, we will let's say p equal what we have in the denominator. Differentiating, we get dp equals 2a dA, and a dA equals half of dp. Doing the same thing here, maybe we'll let q equal b squared plus a half. And so dq equals 2b dB, which means b dB equals half of dq. over here, for these two integrals, we will let this variable here, a, be 1 over root 2 tan of alpha. That means dA equals 1 over root 2 secant squared alpha d alpha. Likewise over here, let's let b equal 1 over root 2 tan of beta, which tells us that dB equals 1 over root 2 secant squared of beta d beta. So lots of substitutions to work with here. Okay, so let's see what we get. Negative 1 over root 2 times, in our first brackets, here ADA is half dP. Here, what do we have? Well, P. A squared plus a half, we let that be P. Plus, what do we have here? Well, first, we'll bring out this numerator. So we're left with 1 dA in the top. So we'll replace it with this. 1 over root 2 secant squared alpha d alpha all over, well, a squared, what happens if we square this? This is a. We get a half tan squared of alpha plus a half. But in fact, if we factor out a half from here, we get half times tan squared plus 1, which is half of secant squared. So this can be replaced by half of secant squared. This takes care of our first bracket. Plus 1 over root 2 times the second big bracket. What we did here, we'll do here. B dB is half of dq over, well, b squared plus a half is just q. Plus our next integral, we have this 1 over root 2, which we'll bring out to the front. And we're left with 1 dB up top. Well, dB is just 1 over root 2 secant squared of beta d beta. And this is divided by b squared plus a half. Well, just like we did over here, if we square b, we get half of tan squared. So half of tan squared plus a half. Factor out a half, that's half of tan squared plus 1, which is half of secant squared. And so we're done with that. So let's see what we have going on here. These secant squares cancel, and so do these. So what are we left with? Some things look a lot cleaner now. We have negative 1 over root 2 times, here we have half the integral of 1 over p dp. Well, the integral of 1 over p is just the ln of the absolute value of p, plus 1 over root 2 of, well, what do we have here? This can come out front, this can come out in the bottom, and all we're left with is the integral of d alpha. Well, what's the integral of d alpha? Just alpha. Moving over to the next bracket, same situation happens. This half comes out in front of the integral, and we're left with the integral of dq over q. Well, what is the integral of 1 over q? It's the ln of the absolute value of q. Over here, again, we have this factor of 1 over root 2, but we can pull out another factor here, as well as this half in the bottom, and then we're left with the integral of d beta. Well, when we integrate that, we're left with beta. So now we're in a pretty good spot. We're almost there, but we'll need some more room. So let's go to the next board. So here we are now back at the next board. And just to note, we did carry out our integrations of all those indefinite integrals. So we should have added a constant at the end of all that. So there it is. Okay, let's keep going. We're going to work backwards now. And let's see what we have. We have half ln of, what was p? It was a squared plus a half. What was alpha? Well, from this substitution, root 2a equals tan alpha. So alpha is the tan inverse of root 2a. That's in our first bracket. Plus 1 over root 2 times half of ln of q, but q was b squared plus a half, plus beta. Well, beta is obtained from here. It's the tan inverse of root 2b. Now let's keep going. We have the following. Let's color code just to keep track of things. Right here, what does that give us? Well, we have half ln of, what was a? A was u plus 1 over root 2. So that squared plus a half, plus this here. We have tan inverse of root 2 of a. But root 2 of a, or a, is just this. So if we multiply root 2 by these two quantities, we get root 2u plus 1. So there's our first square bracket, plus, for the next square bracket, we have 1 over root 2 times, let's look at this term here. We have half the ln of b squared plus half. b was u minus 1 over root 2. u minus 1 over root 2, so squared, plus a half, plus this term here. We have tan inverse of root 2b. So root 2 times this. Root 2 times that, and root 2 times that gives us root 2u minus 1. So there's our second square bracket. Okay, let's clean up what we have so far. In pink, we have half ln of, well, let's square this. That's u squared plus 2 over root 2u plus a half, but 2 over root 2 is just root 2. And then in blue, we have what we see here. So there's our first square bracket, plus, in the second square bracket, we have 1 over root 2 times, in green, half the ln of, well, again, if we square this, it's like what we did here when we squared that, except there's this minus sign. So we'll have u squared minus root 2u plus a half, plus what we have in orange, and we won't touch that just yet. And there's our second square bracket. Okay, we're getting there. So our integral with the variable u is now rewritten like this in terms of u. So we're going to try to take everything back now to our variable x. We'll need some more room, so let's try one more board. Here we are now on what's hopefully our last board, so let's continue. Let's distribute this in. 1 over 2 root 2 times the ln of u squared plus root 2u plus 1 plus minus 1 over root 2 tan inverse of root 2u plus 1 plus, let's distribute here as well, 1 over 2 root 2 ln of u squared minus root 2u plus 1 plus 1 over root 2 tan inverse of root 2u minus 1. Okay, well, this term and this term, if we factor out a 1 over 2 root 2, we will then have this quantity minus this quantity in brackets. But by laws of logarithms, if we're going to subtract those logarithms, we might as well divide their arguments. So we end up with u squared minus root 2u plus 1 divided by u squared plus root 2u plus 1. And then, with these tan inverses, we can factor out a 1 over root 2. And what we'll end up with is this tan inverse plus this tan inverse. So are there any identities that can help us with adding tan inverses? Well, one trig identity we know is that if we take the tan inverse of one argument plus the tan inverse of another argument, that's just the tan inverse of the sum of those arguments divided by 1 minus the product of those arguments. Well, these arguments are conjugates, so we'll multiply this and this to get 2u squared, and 1 and minus 1 to get minus 1. Okay, good. So over here now, we can write u, which was the root of tan x, squared, is tan of x, minus root 2 times root tan x. That's root of 2 tan of x. And downstairs, same idea. Plus, over here, 1 minus 1 is 0. Root 2 plus root 2u is 2 root 2u. So 2 root 2u. All divided by 1 minus 2u squared plus 1. That's 2 minus 2u squared. Or in other words, 2 times 1 minus u squared. These 2's cancel. And that u down here is just the root of tan x. So if we square that, we get tan of x. And so, to brush this up, we have 1 divided by 2 root 2 times the ln of tan of x minus the root of 2 tan of x plus 1 divided by tan of x plus root of 2 tan of x plus 1 plus 1 over root 2 tan inverse of, this is 1 radical, root 2 tan of x divided by 1 minus tan of x. Phew, and I think we've done it. So, we should technically write that after we've made our substitutions for u here, that this integral at this step is the integral of tan of x, the root of tan of x dx. And so, finally, after all this work, we see that the integral of the root of tan of x dx is this. And I think we are done. Thank you.